Welcome to the continuation lecture on cement. In the earlier lecture, we had discussed about the basics of cement. That means what is meant by cement, how many types of cement are there. In this lecture, we will be basically discussing the manufacturing process of cement. So coming to the manufacturing process of cement, mainly three steps are there. First one is mixing and crushing of raw materials. That means silica, alumina and calcium oxide, these will be mixed and crushed. And in the second step, burning of these materials. Burning of these materials will be done in rotary kiln. And third step is grinding. And fourth one is packing. So coming to the first step, mixing and crushing of cement while preparing the cement. So this manufacturing process, we are discussing the wet process. Here, limestone is crushed, powdered and stored in silos. Clay is washed with water to remove organic matter and stored in basin. Both these materials are mixed in grinding mill to form slurry. The slurry contains 38 to 40% of water stored in correcting basin. Coming to the second step, burning process. Here, slurry is burnt in rotary kiln where actual chemical changes takes place. So this is the rotary kiln. Here this is the inlet zone, this is the safety zone, this is the upper transition zone, this is the centering zone, this is the lower transition zone, and this is the outlet zone. Here, this rotary kiln is a steel cylinder. The length of this cylinder is 30 to 40 meters and the diameter of this cylinder is 2 to 4 meters. And this cylinder or rotary kiln can be rotated at the desired speed. The crushed material will be fed into the rotary kiln. So from the upper end, the raw material will be fed into the kiln, and as the rotary kiln is rotating slowly, the material will be coming to the lower end. Here this rotary kiln consists of mainly three zones: drying zone, or it can also be called as evaporating zone, calcination zone and clinkering zone. In the clinkering zone, the main reactions takes place. So coming to the first one, drying zone. The upper part of the kiln is known as drying zone, and the temperature in this zone will be around 200 to 500 degrees centigrade. Most of the water gets evaporated from the slurry by means of hot gases. Coming to the second zone, calcination zone. This is the middle zone of the kiln. With temperature around 700 to 1200 degrees centigrade. Organic matter burns away and CaCO3 will be decomposes into quick lime and CO2. So like this decomposition takes place. CaCO3 will be decomposed into lime and CO2. So this is the picture of rotary kiln. So from here we will be taking the cement slurry which is mixed and crushed. It will be sent into the rotary kiln. This rotary kiln is lined with refractory bricks, and as earlier I told you, so these are the three zones of the rotary kiln: evaporating zone, calcination zone and clinkering zone. So in evaporation zone, drying takes place, evaporation of water, and in calcination zone, decomposition of CaCO3 takes place, and in clinkering zone, the main reactions will take place. Here, hot air will be passed through the powdered core or oil. So here clinkers will be formed. These hot clinkers will be cooled here. So here cool clinkers will be formed. So these clinkers will be used for grinding. So coming to the third zone of refractory kiln, clinkering zone. This is the lowest portion of the kiln with a temperature of about 1400 to 1600 degrees centigrade. Lime and clay nodules melt with chemical fusion and gives calcium, aluminates and silicates. These silicates and aluminates then fuse together to form small hard stones called clinkers. So now I will show you how these clinkers will be formed. Here lime combines with silica and forms dicalcium silicate. We can simply denote this as C2S. Similarly, in clinkering zone, tricalcium silicates will also be formed. This we can show in this way. Similarly, tricalcium aluminates are also formed. Lime reacts with Al2O3 and forms tricalcium aluminate. This tricalcium aluminate can be shown as C3A. In addition to this, tetracalcium aluminoferrate is also formed. So this is called as tetracalcium aluminoferrite. It is denoted as C4AF. So these are the major reactions that will be taking place in the clinkering zone. Now coming to the third step, grinding. So in grinding, cooled clinkers are ground to fine powder in ball mills. At final stage, grounding of about 2 to 3% of powdered gypsum is added. Gypsum is added to avoid setting of cement quickly. And gypsum acts as retarding agent for early setting of the cement. So here tricalcium aluminate will be reacting with gypsum. Gypsum means CaSO4 7H2O. So it will be forming C3A XCO4 7H2O. This is called as tricalcium sulfoaluminate. This is an insoluble compound. Here in the earlier step already I told you how this tricalcium aluminate is formed. Next, packing. Here ground cement is stored in silos, and from silos they are automatically packed into bag of 50 kgs. Next, the parameters to characterize the clinker formation. There are 3 parameters for characterizing the clinker formation. The 3 parameters are lime saturation factor, silica ratio and alumina ratio. So coming to the first factor, lime saturation factor. Here the ratio of CaO to the other 3 main oxides is determined. By applying this to clinker, lime saturation factor can be expressed as calcium oxide by 2.8 silica plus 1.2 alumina plus 0.65 Fe2O3. This is also referred to as percentage, so that's why it will be multiplied with 100. The lime saturation factor controls the ratio of halite to belite in the clinker. A clinker with higher lime saturation factor will have high proportion of halite to belite than with a clinker with low saturation factor. Some typical lime saturation factor values in modern clinkers are 0.92 to 0.98, 92% to 98%. Why means it is in general referred to as percentage. And the lime saturation factor calculation can be applied to Portland cement containing clinker and gypsum if it is subtracted from CaO content, that means lime content. Coming to the second characterization factor, that is silica ratio. Silica ratio is also known as silica modulus and is defined as the ratio of silica to sum of alumina and ferric oxide. A high silica ratio means more calcium silicates are present in the clinker and less aluminate and ferrite. Silica ratio is typically between 2 to 3. Coming to the third characterization factor, alumina ratio. The alumina ratio is defined as the ratio of alumina to ferric oxide. It determines the relative proportions of aluminate and ferrite phases in the clinker. In ordinary Portland cement, the alumina ratio is usually 1 to 4. The silica ratio is between 2 to 3 and alumina ratio is between 1 to 4. Now coming to the properties of cement, setting and hardening. Setting. Setting means stiffening of the original plastic mass due to the formation of turbermonide gel. It can be divided into two stages: initial set and final set. So initial set is when the paste beginning to stiffen, and final set means what? Paste beginning to harden and able to sustain. Now hardening. Hardening is the development of strength due to the formation of crystals with some loads. And here this shows the sequence of setting and hardening. See, when cement is mixed with water paste, in the first day, tricalcium aluminate and tetracalcium ferrate hydrated forms will be formed. And on the 7th day, gelation of the tricalcium silicate takes place. And after 28th day, gelation of dicalcium silicate and tricalcium silicates takes place. That means in the first 7 days, setting process, and for hardening, it will take 21 days. So totally 28 days time it takes place for setting and hardening. So coming to day 1. In day 1, when cement is mixed with water, hydration of tricalcium aluminate takes place within a day. And within 1 day, it becomes rigid, which is known as initial set or flash set. So tricalcium silicate combines with water. So due to this, 880 kilojoules per kg of energy will be released in the form of heat. And to avoid the early setting of tricalcium aluminate, gypsum is added, which acts as retarding agent. So to this tricalcium aluminate, gypsum will be added. Next, from second day to 7th day. So after hydration of C3A and C2S, that means tricalcium aluminate and tricalcium silicate, they begins to hydrate to give tobermonoid gel and crystalline calcium hydroxide, which is responsible for initial strength of the cement. So here I will show you the formation of tobermonoid gel. So this hydration of tricalcium silicate gets completed within 7 days. That means this is called as final set. So here tricalcium silicate, 2 molecules of tricalcium silicate will be combining with water and forms (3CaO, 2SiO2 plus calcium hydroxide plus energy. So this is called as tobermonoid gel, and this is the crystalline calcium hydroxide. This tobermonoid gel has high surface area Next, after initial hydration of tetracalcium aluminoferrate, hardening takes place through crystallization along with dicalcium silicate. Next, tricalcium aluminate combines with water rapidly with evolution of large amount of heat. Combines with water with evolution of large amount of heat. Here this hardening also we can show. Tetracalcium aluminoferrite reacts with water and forms tricalcium aluminate plus tricalcium aluminate 6H2O plus Al2O3 Fe2O3 H2O plus 420 kilojoules per kg of heat will be released. So after initial set, the paste becomes stiff. So adding gypsum retards the dissolution of tricalcium aluminate by forming insoluble calcium sulfoaluminate. So tricalcium aluminate reacts with gypsum and forms insoluble calcium sulfoaluminate. Here already I told you C3A means tricalcium aluminate. So the above reaction shows how gypsum retards the early initial set of cement. When cement is mixed with water, hydration, hydrolysis and gelation reaction starts and some heat is liberated. On an average of 500 kilojoules per kg of heat is evolved during complete hydration of cement. Thank you.